Hello. Let's wrap up our graph theory unit with trees today. We'll talk about what trees are in respect to graph theory, and then information will also help you to finish up your project with the dream vacation that you're going to take in your project world. All right, so in graph theory, what are trees? Well, if you've ever done a family tree, then you have an idea of what a tree is in graph theory also. But before we get there, let me just mention another mathematician that you definitely want on your mathematician list. I had mentioned him previously, but here's more info about him. Solomon Lefschetz. He is the one who coined the name topology. I mentioned this a while back when we first started talking about topology. One of his papers, he coined that term. He was a remarkable person. He was a scientist, and there was a lab accident that caused him to lose his hands and forearms. And after that, he didn't let that get him down and quit. Instead, he just changed gears, and instead of doing science, did math. And then at the ripe age of 81, established and directed a group of 17 research scientists to help close the gap in the space race. Back, many of you are too young to remember, but U.S. and Russia were definitely in a heated race back in the 60s. With space. It wasn't always us working with them to get up to the space station. That's to me, that's a more modern development. So the U.S. was trying to. Russia seemed like they were ahead for a while. Finally, the U.S. kind of caught up and then beat Russia to putting a man on the moon. But anyways, so Solomon Lefschetz was a person involved in that race, and then even later than the ripe age of 81, ended up being awarded the National Medal of Science. Okay, so enough about him. Let's go back to trees. In topology terms, graph theory terms, a tree is a connected graph in which each edge is a bridge. So it's connected. It only has the one component, and all of the edges are important. Like if you took any edge out of a tree, suddenly there would be a disconnected graph. If you think about that, like in a family tree, the edges are all the connections between family members. If you were to take an edge out, then that would mean this whole piece of tree now is no longer related to the rest of the family, which doesn't make sense biologically, but that's the idea on those graph theory trees. There's no redundant connections. You're not going to be able to do any kind of circuits on a tree. That wouldn't make sense either. And humans, anyways, you can't have a circuit in your family tree. So, the spanning tree, we'll get to those two. They call that a type of subgraph. It's a tree created from another graph by removing edges. So you might have a graph that's not a tree to begin with, but you can create a spanning tree by removing edges until you're left with a graph theory tree. Can't remove a bridge because then that would make the graph disconnected. You want to keep the graph connected. You just want to make it to where there's nothing redundant. Subgraph is like a graph you can make from the original graph. Kind of like subsets are sets made from an original set. Same idea. Okay, so let me sketch out a few trees and just kind of sketch out a few things and point out some things about trees. So I mentioned family tree. So if you think about how family trees are made, you might have all these different branches. And then like each node is a person. But if you think about the format of them, they can look a lot. They can have some interesting looks to them. Or if you think about like the bees, remember how we did that with Fibonacci? How the bee family tree. We had to study the Fibonacci sequence. Or there's all kinds of things that you can think about with trees. But the key here, this thing I sketched here is not necessarily a family tree, but the thing I sketched here, notice that, it has vertices, it has edges, But if I removed any edge, then all of a sudden it would become disconnected, and there is no way to make a circuit with that particular tree. Here's another one. I'll sketch another tree just so you can kind of see what they look like. This one has vertices A, B, C, D, E, F. And even though you see like A, E, and B, D intersecting, remember if there's no vertex drawn there at the intersection, then those don't actually touch. It's kind of like an overpass, highway overpass. But that's a tree. If you try to remove any of the edges, suddenly that graph would become disconnected. Like if I try to remove this edge here, that ended up removing too many edges, but see how the graph becomes disconnected suddenly when I remove that edge? So that edge is important to keep it connected. And you could do that with any other edge. Even if you tried to remove like this edge EF, that is a disconnected graph. You can have just a vertex making the component of a graph. But anyways, put that edge back in, it's back to being connected. So those are some examples of some trees. Then a spanning tree, like I said, is made when you take an existing graph that's not a tree and you make a subgraph of it that is a tree. That's called a spanning tree. So let me draw this graph. So we have UVXT, and then we have W. So that one is not a tree right now, because notice you can make circuits. Like you can go from U to T to X to V to U if you wanted to. You can make a circuit. You could go from W to V to U to W. So those are existing circuits that are possible there. So we want to make spanning trees. We don't want them to have circuits available. So let me redraw the graph. And then a spanning tree can be made by erasing some edges. But you don't want to make the graph disconnected, you just want to make it a tree. So let's say I move this edge here between U and V, and let's say I move this edge here between T and X. I still have a connected graph. All of my vertices are there. There is a path from in between any two vertices in that graph. Like to go from T to X, you can get there. Just have to go from T to U to V to W to V to X, but still you can get there. And then now any edges that remain are bridges. Like if I try to erase any more edges at this point, like if I tried to erase this edge here between the V and X, all of a sudden it's a disconnected graph. So that edge needs to stay. But that's not the only spanning tree I can have. That's kind of the neat thing is I can make multiple spanning trees actually from this graph. I'm not going to make them all, but I'll just give you an example that I could make another one if I wanted to. A different one than the one I just made. One that doesn't look like an M so much. Oh, let's see here. What can I erase? I love doing these in class when people can tell me, hey, erase this and let's see what happens. Dang it. I was just trying to erase UW. Alright, so still a connected graph, but still not a tree, because I can still do a circuit. So what if I erase this edge here? Alright, that works. Every edge that remains now is a bridge. If I try to remove any more edges, I'm going to have a disconnected graph. Alright, let's do one more. So these are all spanning trees these are all subgraphs of the original graph. They're all spanning trees. A type of subgraph. Spanning trees aren't the only type of subgraph, but it's the kind we're doing. Alright, so back to this again. Here's the original. And then what can I erase this time? Let's see. What if I erase this one? And what if I erase this one? There you go. So vertices are still all connected. It's a connected graph. There's a path from between every pair of vertices. And it's now a tree. I can't erase any more edges because then I would have a disconnected graph. So there's another spanning tree, another subgraph of that original graph. Some practical uses for this include having maps of telephone networks, email networks, old-fashioned telegraphs, even snail mail. You know, if you think about it, your mail is supposed to come to your box. It's not supposed to go to your box and then take off again and take a circuit. Sidewalk coverings. I used to actually have a project in this class that I don't do anymore, but I would have students take the map of the Winter Haven campus and then use the buildings as vertices, and then for every building, every connection between buildings that had a sidewalk, I'd have them draw an edge. And then have them figure out like a minimum distance spanning tree to get around the Winter Haven campus. Cool thing is, like the Winter Haven campus, when it was in its younger days, I think now there's no coverings now to get to like some of the modular buildings, but before all that existed, just when the main buildings were there, enough sidewalks were covered so that you could get between any two buildings and stay dry during a normal rainstorm. And that's a common thing, like when you're building campuses, is you're going to find a minimum cost spanning tree, and then out of your sidewalks, and then use that to cover your sidewalks and make sure people stay dry. You want to have covering. You want to have a way to get between every pair of buildings, but you don't necessarily want to spend more money than you have to. So you do a spanning tree to help you figure that out. All right, speaking of which, minimum cost spanning tree is the least expensive spanning tree of all spanning trees under consideration. I say this in regards to money, but you could also be thinking distance. Like your cost could be your distance you have to travel. So it could be your shortest spanning tree of all spanning trees under consideration. And there's something called Kruskal's algorithm that helps us to step-by-step construct a minimum cost spanning tree. So a very specific type of spanning tree. And you have to start with a weighted graph to do this. Kruskal's algorithm looks a lot like something we were just doing when we were talking about Hamilton paths and circuits. I don't know if you remember, but we had the brute force method for finding the cheapest route and the traveling salesman problems. But then we also had the approximation methods of nearest neighbor and then cheapest link. Well, Kruskal's algorithm is a lot like the cheapest link method, except we're trying to find a tree and not a nice circuit there. We do not want circuits in this situation. But we can start with just the vertices and then choose the lowest cost edge. And then choose the next lowest cost edge, choose the next lowest cost edge. We just don't want to form any circuits. But with trees, you can have more than two edges coming out of a vertex. A little different than when we were doing Hamilton circuits. In this, you can have more than two. You can have three sprouting out of the same vertex, and that's okay, as long as you don't have any circuits. And the spanning tree is complete once your graph is complete, once you're able to get between any two, once you've got some kind of connections between any two pairs of points. All right, so let me do an example of how this would work. Let's say we start with the original graph. It looks like this. Okay, we're talking A, B, C, and D. I like to change color when I'm writing in the numbers. It's a weighted graph, so I'm going to put weights on each edge. I don't know if you can tell, but BC has a weight of 50. I should erase that. Try it again. Okay. So there's our weighted graph, and we're interested in making a minimum cost spanning tree. So we would start again with just the vertices. It's a lot like that cheapest link algorithm in that regard. And then we would look at what is the lowest cost side. We have a 30, a 45, a 50, a 35, and a 40. 30 is the cheapest. So we go ahead and connect that. So we have a 30. Then out of 40, 45, 50, and 35, 35 is the next cheapest. I don't have to worry about it being connected just yet. Just at the very end, it's going to have to be a connected graph, and it has to be a tree. All right, and then out of the remaining sides, we have a 40, a 45, and a 50. 40 is the cheapest. It does not make a circuit, and we can stop there. Add those up. I believe you get 105. Yep, that's your total weight. 105. And that's it. That was a minimum cost spanning tree. I'm going to have you guys do that with your vacation one. You're going to draw your 5 vertices, and then starting with your lowest cost edge, start adding edges. If an edge is going to make a circuit, skip it. Don't use it. Otherwise, keep going until you have a tree. Until you have a connected graph with no circuits. Let's do another one of those. This one's going to be a more complicated graph. I figured, hey, let's throw you a big one. Okay, the vertices are A, B, C, D, E, F, G, H. And it looks like they skipped I, which sometimes that's annoying to try to keep track of anyways. J and K. And then we have edges AB, AC, BC, AK, CK, CJ, CD, DH, JE, DE, EF, FH, and FG. And then our weights, we have a 7, a 3, a 12, a 5, a 6, a 9, a 15 for this big one, a 17 for this big one, a 4, an 8, 10, and a 2. All right, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 edges, right? Or did I miscount that? Let me make sure. All right, 2, 10, 8, 4, how about I just counted it? 17, 15, 6, 9, 3, 5. Oh, I didn't mark this one with the 11 up here. That's what I'm missing. Yeah, 13 edges, 13 weights. All right. So to pursue our minimum cost spanning tree, I'm going to redraw this with just the vertices for now. I'm not going to connect dots until I can see what's going on with numbers here. And let's do that so I don't start confusing which one's which. All right. So out of all those numbers, I have 7, 12, 3, 11, 5, 6, 9, 4, 17, 15, 8, 10, and 2. 2 is the smallest, so we'll go ahead and connect FG. So we know we're dealing with a 2. And I'll start keeping track of the numbers over here because we're going to want our total weight when we're done. What's next? Let's see here. It looks like 3 is the next smallest between A and C. So I'll connect those and put a 3. And then a 4 between D and E. I haven't made any, nothing's connected yet, and that's fine. We'll keep going. Eventually this will be a connected graph. I have a 5 between K and C. And nothing's threatened to make a circuit yet, so that's all right. I have a 6 between C and D. Okay, that's fine. Uh, 7 between A and B. That's fine still. 8 between E and F. Well, that's fine. Let's see. I have a 9 between C and J. That's fine too. So you notice that C now has a degree of 4. That's fine. With the tree, you can have, unlike the Hamilton circuit, with trees you can have, degree of 3 or 4. That's fine. That was 9. 10 is over here. Oh, that one's good. And now I have a fully connected graph. So I am done. Every single edge that's on there is a bridge. Like if I went back and removed any of these edges, it would be a disconnected graph. It wasn't connected until I got to this point. There's no circuits, so it's a fine tree. And if I add up those numbers, 2, 3, 4, 5, 6, 7, 8, 9, 10, that worked out nicely. I get what, 54? Yeah, that's the total weight. 54 is the total weight of that particular graph, that particular minimum cost spanning tree. Pretty neat, isn't it? Like I said, if you find that you're going to have an edge that causes a circuit, you just skip it and go to the next one. Just like when you were doing your previous Hamilton circuits, except now you don't want a circuit at all, and it's okay to have more than 2 edges sprouting out of a vertex. All right, so now you can wrap up your project, because that was the last piece of it, was to take your weighted graph and make a minimum cost spanning tree, just to see what would that look like on your trip. All right, well, thank you for joining me. Hope you've enjoyed this. In our current text, our next unit should involve financial math, so tune in again soon to learn about the math behind buying a house or a car, something like that. But this is the end of graph theory, so you have a project and a test to wrap up, and I look forward to seeing you again soon.